This video discusses the variation of the internal energy with temperature. The internal energy is the key thermodynamic variable in the first law of thermodynamics, and it's important because it allows us to do the bookkeeping of energy in any system, chemical or otherwise, that we're interested in, and that can be a cell, it could be a heat engine, it could be any system that you really want. Okay, so it's quite interesting and important to realize what the dependence of that thermodynamic variable, the internal energy, is with temperature. Okay, we're going to do this by examining everything that we know about this internal energy. Okay, if we use the first law in differential form, we know that that first law is just the change in internal energy is just the change in heat and work. Okay. All right. So the or the balance of the energy is transferred as heat and work. Now, at the same time, in a prior video, we also have said that it's convenient to express the internal energy as a function of the volume and temperature. And from here, we've been able to show that the total derivatives of the internal energy then would be as follows, right? It would be the first derivative of the internal energy with respect to volume at constant temperature times differential V, plus the first derivative of the internal energy with respect to temperature at constant volume differential of T. Okay, so now to study the dependence of internal energy on temperature alone, we want to freeze the other variable, right? So if we say that the internal energy depends on volume and temperature, and we want to study the dependence on temperature, we need to make the volume constant. Okay, so we're going to be freezing that volume. What that means is that this term that you have right here is actually zero. Okay, and then what that means is that your total first derivative of the internal energy with respect to the variables is just what you have right here. Okay, so then our question is, well, how is this useful? What is it that we can learn? Okay, well, so now we go back to the top expression and we recognize that at constant volume, there's actually no work, right? So the idea is that this term at constant volume becomes also zero. Okay, and then that gets a subscript differential of Q sub V to just signify that we're working at constant volume. Okay, so then what we have here is that we can actually continue to develop that expression and say, well, differential of U is going to be equal to the differential of the energy transferred as heat, which is C sub V differential of T. Okay, and that's what that's the amount of energy transferred as heat when you're working at constant volume. Okay, so if now we compare this expression with that expression, we automatically recognize what this first derivative is, right? It turns out that the first derivative of the internal energy with respect to temperature at constant volume, that is simply the heat capacity of that particular substance at constant volume. Okay, this is very important because it actually tells you exactly how the internal energy depends on temperature. As a matter of fact, because this is the first derivative, this heat capacity at constant volume is going to be the slope of a line tangent to the representation of the internal energy with respect to temperature. Okay, so let's actually draw that. Okay, now if you want to represent how the internal energy changes with temperature, okay, this is going to be a representation, but the slope of that representation is just going to be the heat capacity at constant volume for that substance that you're studying, how the internal energy depends with temperature. Okay, notice that the heat capacities are always positive. Okay, when you supply energy as heat to a system, the temperature goes up. That means that the heat capacity is positive. So you're going to have a graph that looks like this. Okay, and again, a key is that a slope of a line tangent to this representation. Okay, that slope is simply going to be the first derivative of the internal energy with respect to temperature, which is the same thing as the heat capacity at constant volume. Okay, so that's how the internal energy depends with temperature. Is just the heat capacity at constant volume. Now for numerical problems, what we're going to be using is an integrated version of this expression, right? So we take that expression, which we can actually write it here, and then integrate to find an explicit dependence of the internal energy and temperature. Okay, so when we integrate both sides of this expression, then you're going to have the following. Differential of T from T1 to T2. Okay, so this will be a universal expression that we can use for any system. This is always going to be true. Now, in general, there's going to be two cases that we're going to have to consider. And the only difference is whether the heat capacity at constant volume depends with temperature or it doesn't depend with temperature. Okay, so generally, the heat capacity of a substance depends on temperature, right? So it's not the same to supply 10 kilojoules of energy as heat to liquid water at 0 Celsius than to liquid water at 90 Celsius, right? They're going to change the temperature by a little bit, by a different amount, even though the amount of energy as heat that you're supplying is the same. And that's because the heat capacity at constant volume changes, albeit slightly, with temperature. Okay, but it will be a common approximation that we're going to ignore the dependence of the heat capacity on temperature. Right, so if we assume that this number is a constant, then we can just factor it out the integral, and then again, if only this heat capacity is constant with temperature, then we can say that the way to actually study the change in internal energy with temperature is just simply this expression right here. Okay, but again, this only applies if the heat capacity is constant with temperature. If it's not, then we're going to have to solve this integral explicitly, and there will be problems in the homework that will allow you to study that. Okay, so this video has shown to you how to understand the dependence of internal energy with temperature.